Hi, how is everyone doing? My name is Mike Scott. I work at Johnson Space Center in Houston in Mission Control. I'm a power resource officer, otherwise known as a power analyst, and my job is to make sure that we have all the power that we need to run everything on the station, or if we don't, I recommend what things get turned off or how to shift power around. It's something we have to do every week. There's always something that comes up, and we'll talk about that shortly. The mission control room looks like this for Space Station, and this is the room where I work. This is me on console last year, and it's one floor above the mission control room that you see on TV. They don't have TV cameras in my room. So I don't really have a script, but I do have some images because I'm a visual learner, and I thought it would be good to just go through some pictures and describe kind of what I do that way. I thought maybe some of you would enjoy seeing that instead of just watching a talking head. So let's go through some of these. So just for those who don't realize how big the station is, it's about as big as a football field. It's the largest space station, largest spacecraft that people have ever put up, and it was mostly assembled in orbit. And the solar arrays that generate all of our power are the blue things on the left and the right sides of this image. We don't have any other way to generate power other than these solar arrays. And this is a animated graphic of what it looks like when the solar arrays are tracking the sun. This is an older animation because it's got a shuttle docked, and we haven't flown shuttles up there since 2011. But you can see the solar arrays are pointed directly at the sun, the lighter blue side in this graphic. The sun's about to set. You can see they're pointing. You can see the sun angle with the yellow vector when it comes back around. Now the sun's below the horizon and the station is in darkness, but the solar arrays continue pointing at the sun even though it's on the other side of the world because it knows where the sun is. And then the sun rises here and they're pointing at the sun, and we're generating power on the solar arrays. Now we have batteries that store that power when we're not in sunlight. When we're in the shadow of the Earth, otherwise known as night, the batteries supply the power for everything. So this is just a great shot from one of the Soyuz crews that was coming up. And they circled around the station, took a lot of photos. This is one of my favorite photos. The gold is the Kapton tape on the back of the solar arrays. That is not the power generating side. And this is what's currently up docked to station. We've got several visiting vehicles. And visiting vehicles are important for power because we have to park the solar arrays where they don't track the sun when certain ones when visiting vehicles come up, because the rocket plumes can damage the solar arrays. So we call that feathering the solar arrays. These are some of the vehicles that can come up. Not all of them. And this is an example of what I was talking about. You can see how the solar arrays are kind of pointed down, edge on to the vehicle that's approaching, and that's to keep them from getting damaged from the blast from the little rocket motors on the spacecraft that's approaching. Also, we have shadowing on the solar arrays from the vehicle itself. So we have arrays can shadow other arrays, and we can have modules that shadow the arrays. You can see a module casting a shadow on the array, so it's decreasing its power output just from that shadow. Not significantly in this case, but there are cases where it is significant. Also, during certain times of the year, during high solar beta or low solar beta, I'm not going to spend time explaining this graphic. You can pause the video and look it up on Google. But basically, what happens is the sun hits us from one or the other side, and it causes because the station is in a fixed attitude. It causes the solar arrays and the modules to severely shadow the solar arrays, and you'll see that in this graphic here. This is at high solar beta, and you can see that some of the solar panels are in front of the, I'm calling them solar panels just because that's kind of a term that people know, but we refer to them as solar arrays. They're shadowing each other, and the modules are passing in front of the solar arrays, which severely decreases the power on those back ones. So our station power is just about cut in half during this time of the year. And this is also from the point of view from the sun, so it's not the other view that we had a while ago. So this is what the sun would be seeing, and the reason we do that is because we want to see how bad it's affecting the shadowing. So the solar arrays are labeled here, so you can see how we refer to them. There are 8 power channels. There's 2 solar arrays per power channel, and they're tied together in various ways, and one of those ways is shown on the bottom of the page. We can shift power around between those channels that way. So if one of them is severely shadowed, we can shift power to another one that maybe not is shadowed. So here's an example. So 2A is parked because we've got a vehicle coming up, so I painted it red. So 2A is red, and we want to shift power because it's not generating very much, because we've got it off pointed. We want to shift power over to these other channels, and we can do that on the bottom there in the green boxes. So usually when there's a vehicle coming or there's some other event that requires us to park an array, we also have to park these sarge joints. There are 2 joints. You have to have 2 planes of motion to track something in 3-dimensional space, kind of like a telescope with azimuth and elevation. Well, we have alpha and beta on the station. So the sarge is for the alpha angle and the BGA is for the beta angle. And so we usually park both of these joints, the sarge and the BGA, when there's an event. So that also limits power on the other channels where the array is not feathered. It's still auto tracking the sun, but it can't have the other range of motion, so power is severely limited there. This is another way to look at the electrical power system. It's simplified. So on top you've got the solar arrays in the green box, and then the DCSUs, which is a power distribution box with the batteries, the little green batteries. There's 1 battery set for each channel. So this is kind of how the system is divided between channels. And then we have these main bus switching units, which can tie. Some of those can tie together. Well, I'll show you that shortly. And then we have these DDCUs, which are just converters that go from they convert the power from high voltage to low voltage. And then on the bottom you've got the distribution boxes and the loads. So like anything that takes power is represented by a dot on here, and there are hundreds of them. This is just a simplified drawing, like payloads and the vacuum cleaner and everything else. So in our earlier example, 2A had bad power generation, and we moved stuff to those other green boxes. This is just showing the same thing. You can see the green boxes there. Those are picking up the power. So also another way we can move power around is by turning off a payload, for example, and using the alternate feed. There are sometimes 2 feeds to a load or science sometimes. So we can, in the red X, you can see that we've turned that off, and we turn on the alternate feed on 1 Bravo, on 1B. This is another drawing that kind of shows how the MBSUs are connected, and we need to do that sometimes. We're going to do that next week for doing a battery EVA, where we're going to change out some batteries. And you can see here that channel 1B is going to be down, or if it failed we could do the same thing. But 1B is going to be down for part of next week, and we're going to tie 1A to 1B inside MBSU 1 with that little 9 that has a circle around it. That'll allow power to flow from channel 1A down to the 1B loads. So the 1A solar arrays will be powering the 1A and the 1B loads. It's kind of cool that we can do that. This is what our batteries do. They charge up in sunlight, and then they discharge when we're in the shadow of the Earth. So all the loads are maintained by the batteries or the solar arrays, and there's about 16 orbits per day, so you can kind of see what it looks like over the course of a day here. And this is our estimated power usage on the channel versus our available power, and you can see that our planned power usage is over our available power during part of this day, and you can see what happens on this next plot here. The batteries start going down. So part of the job of the power planner is to not let that happen and keep things in what they call energy balance, where you're charging up to 100% every time on your batteries. Because if the batteries get too low, they trip off, and then you can lose payloads and lose millions of dollars worth of science and bad things like that. So that's pretty much it. That's the things that we're concerned about as power analysts, as power resource officers, and there's about 8 of us who do this job. You won't see us on TV. There's no TVs in our room, but it's fun. Get to work with astronauts sometimes, and thanks for letting me tell you a little bit about what we do. I wish I had a lot more time. 10 minutes is not very long. And I'll just leave you with my contact information. So nice to meet you. Have a good day.